So we have 4 problems, and there's a couple of little details that might be easy to miss, but overall this is a relatively easy situation. So let's dig in here. So concerned citizen, servant committee investigating injuries to junior high students, committee incidents of high incidence of injuries. You're watching them practice, looking for large horizontal forces on the ankle. So guess what shoemakers think about for hiking boots or basketball shoes, or you name any activity where this is an issue. This is somebody is thinking of this. Some engineer, some designer is thinking about these things. And so we have this, a 40 kilogram student jumps 1 meter straight up. I wish I could do that. And shoots an 8 kilogram basketball at its highest point. And the ball left its hand at 30 degrees and horizontal at 20 meters per second. And so we want to know what's the horizontal velocity when he hits the ground, okay? So what is the horizontal velocity? Well, horizontal velocity will be a Vx thing, which we know would be the initial speed, cosine theta, because we haven't tilted anything. Everything's still relative to the ground. So this is a number that you can compute, and I'm not going to compute it for you because you could just compute it, all right? So there's that piece of the puzzle. Then there is the fact that the momentum of the ball equals the momentum of the player. So, think Michael Jordan, it's the jump, shoot. So there's this push of the ball, and that's going to cause the player to move back. Not just because they're trying to, but you can't help it. You'd have to really fight to not have that result in some backward motion. It'd be much easier to do that in space. You've probably seen space movies where they deal that. And just remember, momentum is always, generally speaking, mv. So you can, if you just use this basic vector, Vx is the initial speed they were given at the cosine of those degrees, and then you can set up, P ball, so M ball, V ball equals M player, V player. Easy. Then this next one here. And so this one we're going to need to use some vector notation that we've used the heck out of in Python, and not as much on paper, but we need to do that. So this is a movie about a hawk that catches a goose, and geese are bigger than hawks, and so we need to pay attention to. So there's this 1.5 kilogram hawk, goose 2.5 kilograms. Let's see. That hawk is going 60 kilometers per hour, and that goose is going 30. And so they collide, and so 2 different momentum systems, system of the hawk, system of the goose, collide. The goose becomes one with the hawk as it sinks those talons into it. And so we want to animate this, etc. So this data that we have, so what do we have? Let's do this. We know that the combined mass is going to be equal to the mass of the hawk plus the mass of the goose. That's the end game of this system. Is there now, as a momentum system, there are combined masses. Okay, initially they're 2 separate objects that become one. And so this is our system, at least the end game of it. And so we know that in that combined system, the x part of that is just going to be equal to mass of the goose, velocity of the goose. And in the y part of it, it's going to be the mass of the hawk, velocity of the hawk. Now this is hawk is driving straight down. That's why it's a y. Okay. Thing. So there. And the goose was just flying north. Okay, so little details to pick out and then to model mathematically, physically in that situation. So this leads to, I want to know the magnitude of a vector, a Vx, Vy vector, and we know that that's going to be equal to, the square root of some squared things, all right? Just the Pythagorean identity on that. Also, you're in this one, I forget whether I asked about the angle. I don't think I asked for the angle. I think I just asked for the speed, the magnitude of the speed, I think. But if we wanted to know that, it's going to be the inverse tangent of y over x components. So hopefully you remember that from pre-calculus days and whatnot. So I wanted to set this up because I don't know that this is the easiest thing to just see at this level of physics. You need to know, why would I think of it this way? And admittedly, thinking about the end game, about the combined, at the end of this, the initial conditions are goose just going its way north and a hawk grabs it. So initially, they're two separate systems, mass systems. Finally, they're one mass system. And I'm going to need to account for that. And so I can define a variable, or I could just say mh plus ng times each one of those. And so this right here is sort of holding onto that end game and knowing that all of the horizontal momentum comes from the goose. All of the vertical momentum comes from the hawk. And these things are going to come together over here. And so if you're going to put Vx and Vy into this magnitude game, you're going to need to finish, you're going to have to solve so solve for this so that it can go in there, and then solve for this so that it can go in there. Then you can do the rest of the story. All right, next problem. 2 down, 2 to go. Here, similar kind of situation. Looking back in time, the hedonist, I think, some ship was going south. So that would be a minus 20, I think it was, 20 knots. We don't even care about the units because, at least double check that. It was going south at minus 20, and then the iron side was going west, minus 10 knots or whatever. And then there was they collided and stuck together as one got lodged in the other, and so that means the final combined velocity would be something off in that distance, in that direction. So if you had this navigational data that was even remotely close to reality, you could kind of narrow your search field to some place out in that direction to go find this treasure on this thing here. So hedonist, 20 knots due south. The iron horse, west at 10 knots. And so those things don't matter there. And then we have, hedonist was 60,000 tons. I'm sorry. Get that backwards. 40,000. 60,000 ton for that. 40,000 for the hedonist. All right. So we'll need those pieces of the puzzle. So again, initial momentum equals final momentum. Initial momentum is where the momentums of the objects that are going to become one and the same are their own momenta, and they're on the final end of it, they will be combined in some way. And so the setup, fundamentally the same as the last problem. I'm going to have the mass of the hedonist plus its velocity. Whoops. Can't add mass and velocity. Mass times velocity of the one plus the mass times velocity of the other is going to equal their combined mass, which I'll just write as big M again, and their final velocity. This has to be true. This is conservation of momentum. And what we can do is we'll just let x, there's really no, and this may seem weird because wait a minute, x, why can't the hedonist be y? It could be. It doesn't really matter when it comes down to it. Man, that screen flicker is irritating. You could switch them up any way you want. And then this is the combined part of it. X and Y, I absolutely wouldn't matter. And I purposely did it the way that's unnatural because sometimes, actually, with more frequency than you realize now, you will not pick a normal coordinate system in real life. Sometimes you will pick usually positive and negative are what you absolutely will not cooperate with. You will make left positive and down positive in certain systems. But other times you might do something like this. This is a stretch though. All right. And so it's again, same deal. Momentum is a vector, which means I can write it this way. And this is the total momentum, which also equals mv. That means you can solve for v. All right? And it's just going to be, I don't feel bad giving this away because it's just algebra. So you can actually know, and you'll get components in this one. And so depending on how I ask the question in Blackboard, you may need to get a magnitude. And inevitably you will need to get a magnitude. You'll need to do that Pythagorean thing to finish that one off. All right? So basically I just gave away how to look at the problem, simple equations, and then I think possibly, there's steps like, how would you decide, this? That is not the most obvious shift, admittedly. So I wanted to say so. You could find examples of that in pretty much any textbook. And then to remember that this vector is the momentum vector, and it has to equal the end game, the sum, the net momentum, if you will, the superposition of it. And that leads to some advantageous things at the end there. All right. One more, and we'll be done. Yay. So in this one, there is an astronaut. Okay. And he's an 80 kilogram astronaut. There is a space shuttle, which I'm exaggerating the relative size, obviously. An astronaut's not quite that big. Here, and there is this distance between them of 200 meters. And in this problem, they're both moving at the same speed, which out in space, that means they would be maintaining that distance. But she's got 4 minutes of air remaining. Her thrusters on her suit don't work, and she needs to get back before she dies. And so she knows, because she took physics, so pretty much any astronaut will have taken physics, because there's no way you're going to get into that sort of game without having some basic knowledge. She says, I will throw my toolkit away, and that will give me a way to change my momentum. Okay, I think I've seen this in, the movie Gravity, Sandra Bullock and George Clooney, I think. And I've seen it in a couple other things where you do that so that you can change your momentum and direct yourself somewhere. And this distance can also be thought of in terms of time, because the time limitation is the 4 minutes of air she has left, which is 240 seconds. All right, so we've sort of encoded for all of the information except for here where she's at. She is going to take a 10 kilogram toolkit and push it away at 8 meters per second, because I guess they train for that. I don't know. Okay, which I suppose they would make a great movie. All right, so we have this. We've drawn a diagram of the system, and we can start thinking about these things. And so here, this is a simple. The initial momentum of the astronaut is going to be her mass and speed. That has to end up equaling the mass and speed of the thing she throws away, which means I can find that new speed that she's going to do. So really, I have P initial equals P final, which is going to be mass speed product of the astronaut, mass speed product of the toolkit. Okay, these have to equal one another. Technically, don't necessarily need to do that. Just need to know that these have to be equal and opposite. Okay, and that means that you can solve for the velocity of the astronaut. Okay, now that won't answer the question. That's just part of the answer. You would have to use the first zeroth law to find out if she makes it. And there's only one thing you won't know in the three variables that are in the first zeroth law. And since you have one piece of information here about that limiting thing, then I'll leave the rest to you. And that, my friends, is a wrap.